So in this class, I will explain about generalized Hooke's law, which is a very important principle in mechanics of deformable bodies. About Hooke's law, all of you know, within elastic limits, stress is directly proportional to strain. So this is Hooke's law. Sigma directly proportional to epsilon, or sigma is equal to E into epsilon, where E is the Young's modulus and modulus of velocity of the material of the object. This is Hooke's law. Now, this of course is valid for uniaxial loading case. Uniaxial loading means if the load is applied only in one direction, maybe tensile or compressive force, if it is applied along one direction, for example, P is the tensile force acting along x direction, we can say. So we can define this Hooke's law. Of course, in your undergraduate DE program, we have done tension test or wide steel specimen, and we have calculated the stress and strains at different points, and you have plotted the graph of stress versus strain. Stress is plotted along y-axis and strain is plotted along x-axis. Stress doesn't have any stress has the units of Newton per mm square, where strain doesn't have any unit. So if you can see, so initially it will be a straight line, graph will be a straight line up to the elastic limit, and then of course depending on the type of material, it takes something like this. All this you have learned in your strength of materials in your undergraduate BE course. Now here, whatever slope is there in this linear portion, this slope tan theta will give the value of Young's modulus approximately for the material of the structure or the specimen. So this is what we studied in SY, strength of materials. Now suppose on similar lines, if the object is subjected to, if the material is subjected to triaxial stress system. Triaxial stress means it is subjected to stress in all the three directions, like this, x, y, z directions. So it will be something like this. So in x direction, in y direction, in z direction, we will be having stresses sigma x, sigma y, sigma z. These are the normal stresses because they act perpendicular to the cross section, in addition to that, we will be having shear stress also. So all these I have explained in the first video. Please go through the first video, stress at a point. So stress at a point, we will be having 6 stress components like the sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx. So these are the 6 components of stresses at a point when it is subjected to triaxial stress system. So stresses are acting in all the 3 directions. So if the stresses act in 2 directions, then it is a 2-dimensional stress system or biaxial stress system. Now let us, this generalized Hooke's law is defined for triaxial stress system. So we will see how we can arrive at the equations. So you have learnt in strength of materials that if mu is the Poisson's ratio, you know that Poisson's ratio is the ratio of lateral strain to linear strain. So within elastic limits, once again, it is a constant. So just like Young's modulus, this is also an elastic constant. So E is the Young's modulus, and you have one more called rigidity modulus, G, or shear modulus. So we know the relationship between these three elastic constants in this form. That is, you can have this E is equal to 2G into 1 plus mu. So all these you have learned in your undergraduate strength of materials course. So 2G into 1 plus mu. This is the relationship between these 3 elastic constants. Now, what I can do here is is, here G is defined as your shear stress divided by shear strain. That means tau divided by gamma within elastic limits once again. Now, when you consider all these three elastic constants, the strains in the three directions, strains I can call them as epsilon x, epsilon y, epsilon z. These three are the strains along the three mutually perpendicular directions x, y, z, subjected to all the three stresses, that is sigma x, sigma y, sigma z. So that we can define. So strains can be defined as, if you consider the effect of Poisson's ratio also, epsilon x is the strain in x direction, net strain in the x direction due to all the three stresses. It can be defined as sigma x by E, sigma x by E minus mu times sigma y by E. So please note that here minus mu times sigma z by E. So if you are writing the strain in x direction, normal stress we have to consider, and we have to consider the normal stresses in y and z directions with a negative sign along with this mu sign, because when it is, the thing here is, when sigma y is tensile in y direction, it expands in y direction, but it contracts in the other two directions, that means x and z direction. That is why we have to take this as minus sign. So this equation gives the effect of both mu and E in x direction. Similarly, you have epsilon y as, on similar lines, sigma y by E minus mu times sigma x by E minus mu times sigma z by E. So this is written on similar manner, and epsilon z can be written as sigma z by E minus mu times sigma x by E minus mu times sigma y by E. So please note that the effect of the other two, the effect of any stress in the other two directions will be opposite in nature. That's why, since I have considered all these as tensile stresses, the effect in the other two directions will be compressive. Now, these three are the equations. Now, what I will do here is, I will add these three equations, 1, 2 and 3. I am going to add. So, adding 1, 2 and 3, adding 1, 2 and 3. So, you will be getting LHS epsilon x plus epsilon y plus epsilon z. So, this can be written as the volumetric strain epsilon V. So, epsilon V is the volumetric strain. So, this also we have learned in your strength of materials. So, epsilon V, I will take it as volumetric strain, which is nothing but the sum of the net strains in all the three directions in the case of a object like this. So, when you add the RHS, you can see all the terms. When you add, you can see here some of the terms are common here. So, sigma x by E plus sigma y by E plus sigma z by E. So, in that I think I can take E outside and it becomes sigma x plus sigma y plus sigma z. So, what I can write here is 1 by E into sigma x plus sigma y plus sigma z. This is what I can get, minus in other terms. So, here you can see minus mu times sigma y by E is here and it is also here. Similarly, sigma x by E is here and also it is here. Sigma z by E is here and here. That means there are two terms. So that means what I can write here is minus 2 mu by E. Okay, 2 mu by E into sigma x plus sigma y plus sigma z. This is how we can write after combining all the 9 terms. So now here once again I can take this 1 by E common. We will be left with 1 minus 2 mu into sigma x plus sigma y plus sigma z. So this is epsilon. So this is another important relation we got. We can take this as 4. So volumetric strain is given by 1 by E into 1 minus 2 mu, that is common here, into sigma x plus sigma y plus sigma z. Now after getting this, what we can do here is I will just take the expression for sigma y plus sigma z here. I want only for sigma y plus sigma z. So this is simplification I have to do. From this, what I do here is sigma x plus sigma y plus sigma z will be equal to, so what I can write, E into epsilon v divided by 1 minus mu. I think we can get like this. Okay, this is what we have. Now this sigma y plus sigma z, only these two terms if I want. So the sigma x goes to this side with a negative sign. E into epsilon v divided by 1 minus 2 mu minus sigma. So let me take this as 5. Now what I will do is, I will take 1 and 5 now. Consider equation 1 now. Consider equation 1. So one states like this: sigma x is equal to, epsilon x is equal to sigma x by e minus mu times, I can write this as minus mu by e times sigma y by sigma z. I can just combine these two terms. Minus I can take as common, so that this becomes plus. Now for this sigma y plus sigma z, I will substitute this 5. Substituting from 5 for the sigma y plus sigma z. So let me see what you are going to get. So epsilon x is equal to sigma x by e minus mu by e into this much, into e into epsilon v by 1 minus 2 mu minus sigma x. So like that we are going to get. Now what I will do here is, I will take take sigma x terms together. So that means I have to switch here now. So this becomes sigma x by e minus, multiply these two, this e will get cancelled. You will be left with mu times epsilon v by 1 minus 2 mu. First term will be this. Then second term will be minus into minus, it becomes plus sigma x into mu by 3. Okay, this is what we get. Now I will combine the sigma x term together. So what I will do here is, I will combine this sigma x term together. So epsilon x is equal to sigma x by e, I can take common, into mu times epsilon v minus 1 minus 2 mu divided by 1 minus 2 mu plus mu. Of course, this mu also I can take common, so it becomes epsilon x into mu divided by e into epsilon v by 1 minus 2 mu plus 1. So something like this we are going to get. So if I want sigma x, therefore from this sigma x will be equal to, if I want this much, this e into epsilon x will be there, divided by mu into epsilon v by 1 minus 2 mu plus 1. So like this. This is what we get. So that 1 minus 2 mu I can always take to the numerator. This into this. Okay, epsilon x is equal to e into sigma x is equal to e into epsilon x divided by mu times, this becomes divided by mu times epsilon e by 1 minus 2 mu plus 1. Now I can always convert this into another form. So 1 plus mu, okay, I will just take this LCM and I will simplify e into epsilon x divided by mu into epsilon v plus 1 minus 2 mu divided by 1 minus 2 mu. Something like this we get. So I want in another form. So 1 by e into sigma x epsilon v divided by 1 minus 2 minus sigma x. Okay, minus mu by e into epsilon by 1 minus 2 mu minus sigma x. Sigma x will be minus mu times, this e, this e of course e will get cancelled, 1 minus 2 mu plus, okay, I will do one thing here. Let me slightly change this because I need it in the standard form. What I will do is, I will do one thing. This, let me 1 by e I will take common here. So that is better. 1 by e into sigma x minus mu e epsilon v by 1 minus 2 mu. Then I take sigma x minus mu into e into epsilon v by 1 minus 2 mu minus because minus into okay. This becomes minus, whereas this becomes plus 1 by e I have taken plus sigma x into v. So I get like this. Then after that, epsilon x is equal to sigma x. Okay. So here, sigma x plus sigma y plus sigma z is equal to e into epsilon v divided by 1 minus 2 mu. This is correct. Epsilon v divided by 1 minus 2 mu. So after that, okay, that we got. Okay, now let me. So what I want here is, I want to take sigma x separately. So this e into epsilon x will be equal to sigma x. If I take common, 1 plus mu I will get minus mu into e into epsilon x epsilon v divided by 1 minus mu. Yes. So now therefore sigma x into 1 plus mu will be equal to e into epsilon x plus mu e epsilon v by 1 minus 2. Simplification. So sigma x will be therefore e divided by 1 plus mu into epsilon x plus mu into e into epsilon v by 1 plus mu into 1 minus 2 mu. I think this is correct. So sigma x is equal to e into epsilon x by 1 plus mu into e into epsilon v divided by 1 plus mu into 1 minus 2. Yeah, this is correct. This is what I have done here is, I have expressed sigma x exclusively in terms of epsilon x and epsilon v. So now after getting this, we can have some substitution here. So here I am going to introduce one constant called Lami's constant, which is this mu divided by. So introducing, so take Lami's constant lambda. I am going to take lambda as mu divided by 1 plus mu into 1 minus 2 mu. This is Lami's constant. Mu divided by 1 plus mu into 1 minus 2 mu. That means Laplace constant depends only on Poisson's ratio. And another relationship we know that E is equal to 2g into 1 plus mu. Therefore, E divided by 1 plus mu will be 2g. So this becomes 2g. E divided by 1 plus mu will be equal to 2 times E. So if you substitute these two things there, therefore sigma x will be now, this is 2g into epsilon x plus this is Laplace constant lambda into E into epsilon v. So this is the relation which relates stress sigma x in terms of volumetric strain and epsilon x. So this is what we get. So sigma x is equal to 2g epsilon x plus lambda into E into epsilon v. Now on similar lines we can prove the expressions for sigma y and sigma z also. So what I will write here is, similarly it can be proved. So you need not prove, you can directly write that. Similarly it can be proved. So sigma y is equal to, so on the same lines you can write sigma y is nothing but 2g into epsilon y, instead of epsilon x, epsilon y will come plus that remains same, lambda E into epsilon b, and also sigma z will be 2g into epsilon z plus lambda E into epsilon b. So the second term, of course, it remains same. So these three, sigma x, sigma y, sigma z, can be expressed in terms of epsilon x, epsilon y, epsilon z and epsilon v. So together, so finally, so what you can combine all these three. So I can call them as so this is 5 and 6. Okay, this is 5 and this is not 5, 6 and 7. So the 6 and 7, they are called as the generalized equations. Equations 6, 7. And also, if you write the stress, shear stress in terms of shear strain, you know that G is nothing but, you can have done here, G is equal to tau by gamma, where tau is the shear stress, gamma is the shear strain. If you write that in all the three planes, you can write that tau xy is equal to G into gamma xy, because tau xy by gamma xy is G constant. It is a homogeneous and isotropic material. So Young's modulus, rigidity modulus, they all remain same in all the three directions. That is the meaning of isotropy. So tau yz is G into gamma yz, and tau zx is G into gamma zx. So these three relations I can call them as 8. So shear stress to shear strain, linear stress to linear strain, or normal stress to normal strain. So equation 6, 7 and 8. So all these put together, they are called, it is called as generalized Hooke's law. So very important relation in elasticity, because it gives the relationship between stress and strain. So this is also called as stress strain relation. Stress strain relations. Of course, in 3D stress system. So using this, we can solve some problems. Knowing this strain, you can find out the stress and vice versa. So they are also called as Laplace equations, because Laplace constant is involved. So lambda is involved. By knowing mu, you can find out lambda. So mu will be 0.3 or 0.25 for steel and concrete. So maximum value of mu is 0.5 that we have learned. So by knowing the value of E and mu, you can find out G also and lambda also. Once you find out the values of G and lambda, we can substitute them in these equations to get the stress values. So by knowing the strain values. So by knowing stress, strain, you can find out stresses or vice versa. So this is how we can use the three equations to find out the stress strain relationship. See, if you know the stress values you can use these three equations 1, 2 and 3 to find the strain values. If you know the strain values, you can find out equations 6, 7 and 8 to find out the stress values. So this is the relation between the stress and strain in a triaxial stress system, that is three-dimensional stress system in elasticity.